Epoxides occur in important biologically active compounds and are widely used in organic synthesis. So it's a good thing there are easy ways to make them. There are two key ways. I'll show you both. Both methods transform an alkene into the epoxide. When you treat an alkene with a peracid, one of the oxygens of the peracid is transferred directly to the alkene to make an epoxide. While there are several different peracids that are used, there are only a few that are common. The few most common ones include peracetic acid and perbenzoic acid. The chemistry works well regardless of the group that's attached directly to the peracid. I'm going to rotate this molecule at 90 degrees so we can get a better look at the stereochemistry. This puts two of the alkene substituents toward us, here on the wedges, and two of the substituents back away from us on the dashes. And now we see as that peracid transfers an oxygen, it makes a three-membered ring with substituents sticking down, two away and two toward us. I'm going to number those so we can track them. The 1 and 4 substituents are both back in the starting material and are both back in the product. And the 2 and the 3, of course, are both toward us in each structure. So the stereochemistry of the alkene is maintained in the stereochemistry of the product. This is a stereochemical result called stereospecific. And the definition of stereospecific is that the stereochemistry of the reactants, the alkene in this case, dictates the stereochemistry of the products. So for example, if we switched 1 and 2, 1 and 2 would be switched in the products. This is a very important aspect of epoxide chemistry and one of the reasons it's so widely used. So peracid synthesis of epoxides from alkenes is a one-step reaction that's stereospecific. Let's look at the other way for making epoxides. This is a two-step process. When bromine and water together are used to treat an alkene, we make a compound called a bromohydrin, as you've seen here. And when we treat bromohydrins with base, they make epoxides. This is an internal SN2 reaction. A pair of electrons on oxygen is used to make the new bond with carbon, as the bromine leaves with a pair of electrons as bromide. You'll notice that this reaction is also stereospecific. This is easy to see when we number the substituents. Both steps are stereospecific, but because in both cases, the stereochemistry of that alkene that we start with dictates the stereochemistry of the bromohydrin, and the stereochemistry of the bromohydrin dictates the chemistry of the final epoxide. And you'll see that the stereochemical result is exactly the same as we got with peracid. When 1 and 4 start back, 1 and 4 end up back, which means 2 and 3 start in front, and 2 and 3 end up in front. Now I've simply written base here by the arrow for the second step. Lots of bases have been used in work. I've written 3 examples here. So, bottom line, alkenes are converted stereospecifically into epoxides. You can use a single-step process using peracid, or a two-step process using bromine and water, followed by base. Both approaches give very good yields and are used widely.